In this chapter, we're going to explore one of the most persistent and frankly damaging vulnerabilities out there in web applications, SQL injection. We are going to open up the hacker's playbook and break down step by step how an attacker can go from a simple text box on a website to having total control of the server it's running on. So here's our roadmap. We'll start at the very beginning with how the flaw is even born. Then we'll follow an attacker's trail as they find their first clue, unlock the doors to the system, and even attack in the dark. We'll see the climax of the attack, total system compromise, and, most importantly, we'll finish up by learning how to build the fortress, the right defense to stop this from ever happening. All right, let's get right into it. Before we can really understand the attack, we have to understand the environment where it lives. Now, a lot of people think SQL injection is some kind of bug in the database software, like Oracle or Microsoft SQL Server, but that's not it at all. The reality is, the vulnerability is born from a fundamental flaw in how the web application talks to the database. At the very heart of this issue are what we call interpreted languages, and SQL is a perfect example. What this means is that the code is processed live, or on the fly. You can think of it like having a live translator. This translator is reading the developer's instructions and the user's input at the exact same time. And because it's doing both at once, it can sometimes get them mixed up. It's this act of mixing that creates the danger. And this slide really highlights that key difference. With compiled languages, there's a hard wall between the program's logic and any data a user gives it. But with interpreted languages, that wall gets blurry. The interpreter is processing everything together, which means it can be tricked. It can be fooled into thinking that some data a user typed in is actually a brand new command it should run. This right here gets to the absolute core of the problem. Think about it like this. The application is building a sentence to send to the database. It starts with something like, find me all the books where the author is, and then it just glues whatever the user typed right onto the end of that sentence. A normal user types a name. But an attacker types something that doesn't just finish the sentence, it rewrites it, twisting its meaning completely. Okay, so this flaw exists out there in the wild, but how does a hacker actually find it? Well, it usually doesn't start with a big, noisy attack. It starts with a very quiet probe, kind of a gentle knock on the door to see if the application is vulnerable, and more importantly, to see how it answers. And that knock on the door is often just one single character, the apostrophe. So why a single quote? Well, in the SQL language, single quotes are basically punctuation. They're used to mark the beginning and end of a piece of text. So by throwing in an extra unbalanced quote, an attacker is hoping to break the grammar of the SQL command. Let's look at this example. The application wants to search for a publisher. An attacker inputs O'Reilly. The application, not knowing any better, builds the query you see here. The database sees the first part, publisher equals O, and thinks, okay, that's a string. But then it sees the rest, Riley. To the database, that's just gibberish. It's not valid SQL syntax, and the whole command just breaks. And what happens when it breaks? You often get an error message, something just like this. Now for you and me, that's an error. But for an attacker, this is the jackpot. This is like blood in the water. It's the first real proof that what they typed in directly messed with the database query. They've just confirmed the application is vulnerable. So the attacker knows the door is unlocked. Now it's time to step inside. Once that vulnerability is confirmed, the attack escalates. And a common first goal is something simple but really powerful, just bypassing a login screen without needing a password at all. This is a classic, almost elegant trick. The attacker inputs the username admin, followed by a single quote. That quote closes the username part of the command. Then they added double hyphen. In SQL, that means ignore everything else on this line. So the database processes the part that checks for the username admin and then completely ignores the part that was supposed to check the password. The password check has been literally commented out of existence. This version is even more of a game changer. Here, the attacker injects a condition that is logically always true, or 1 equals 1. So the query becomes find a user where the username is blank or where 1 equals 1. Well, 1 always equals 1. So this condition is true for every single user in the database. The database happily returns the entire user list, and the application often just logs the attacker in as the very first user in that list, who, guess what, is usually the admin. Bypassing a login is one thing, but that's really just the beginning. The real prize for an attacker isn't getting in, it's stealing everything that's inside. And they're not just limited to tricking the query that's already there. They can actually inject a whole separate query of their own and get all of that data back too. And the attacker's skeleton key for this is the union operator. Now, union is a perfectly legitimate SQL feature. It's designed to let you merge the results from two different queries into one neat package. But an attacker can abuse this to piggyback their own malicious query right on top of the application's normal, everyday query. This slide shows exactly how that hijacking works. The application is just trying to run a harmless search for books, but the attacker's input injects that union operator. It's essentially telling the database, hey, after you go find that list of books for me, I also want you to run this other query to get all the usernames and passwords from the users table, and then just stitch both results together into one big list for me, okay? And the poor application has no idea what just happened. It gets the results back and just displays them. And you can see, right there in the table, mixed in with the actual book titles, are the usernames and passwords from a completely different table. The sensitive data is hiding in plain sight, disguised under columns like author and title. But what if the developers have been more careful? What if they've configured the application so it never shows you a detailed error message and it doesn't display weird, unexpected data? Does the attack stop there? Not a chance. The attacker just has to work in the dark. This is where things get really clever. It's called blind SQL injection. Since the attacker can't see the output directly, they have to be more patient. It's like they're playing a game of 20 questions with the database. They ask a series of simple, true or false questions and just watch for very subtle changes in how the application responds. There are a couple of ways they can do this. With Boolean-based attacks, they ask a question that changes the page. For instance, does the administrator's password start with the letter A? If the login succeeds, the answer is yes. If it fails, the answer is no. Time-based attacks are even sneakier. The attacker tells the database, if the admin's password starts with A, just wait 5 seconds before you answer. If the web page suddenly takes 5 seconds longer to load, they have their answer. It's slow, but by asking thousands of these tiny questions, they can piece together the entire password. So far, we've really been focused on stealing data from the database. But for a determined attacker, that's just a stepping stone. This is where it gets really scary. The ultimate goal, the final boss of this attack, is to take over the entire server. And this is the final, devastating escalation. The attack is about to break out of its cage. It moves beyond just the database and starts targeting the server's underlying operating system. And this becomes possible if the application connects to the database using an account that has way too many permissions. And a great example of this is a feature in Microsoft SQL Server called XP_command shell. Now, this is a powerful administrative tool. It's designed to let a database admin run system commands without ever leaving the database. But it's also like a loaded gun left lying on the table. In the hands of an attacker who's found a SQL injection flaw, this tool becomes a weapon for total system compromise. This is the absolute worst-case scenario. The attacker injects a payload that tells the database to execute XP_cmd shell. In that single moment, the game completely changes. They aren't just talking to the database anymore. They are now talking directly to the Windows operating system. They can list files, read sensitive configuration data, upload malware, and even use that server to attack other machines on the internal network. At this point, it is absolutely game over. The attacker owns the box. Okay, that was pretty grim, but now for the good news. After seeing just how catastrophic this can be, let's talk about the defense. How do we build a fortress that is completely immune to this entire class of attack? A lot of people's first instinct is to try and filter out bad words. You know, they'll try to block words like select or characters like the single quote. This is called blacklisting, and it is a terrible idea. It's a game of whack-a-mole you will never win, because attackers are endlessly creative and will always find a way to bypass simple filters. The only real solution is to go right back to the original sin we talked about, the mixing of code and data. The definitive defense is to fix that fundamental problem. We have to draw a hard, unambiguous line in the sand between our commands and the data that users provide. We need to keep them in completely separate boxes. And the way we do that is with something called parameterized queries or prepared statements. It's actually a pretty simple idea. First, the application sends the database a template of the command with placeholders, like a question mark, where the user's data will go. The database looks at that template and locks it in. Only then, in a second separate step, does the application send the user's data. At that point, it doesn't matter what the user typed. The database will only ever treat it as plain old data to fill in the blank. It can never be mistaken for a command. And you can just see the difference here. On the left, you've got that dangerous approach, where code and data are just mashed together into one big string. It's a messy, vulnerable soup. But on the right, you see the safe, clean, two-step process. First, you define the query with a placeholder. Second, you provide the data for that placeholder. That separation is everything. It makes this entire class of attack impossible. So, after walking through this entire attack, from that first gentle probe all the way to total system compromise, what's the big lesson we should take away from the hacker's playbook? Well, it really boils down to a few key things. First, the core principle. Never, ever trust user input. Assume it's hostile. The flaw is born from that dangerous mixing of code and data. We saw the attacker's clear path: probe, bypass, extract, and escalate. The absolute best defense is to use parameterized queries to enforce that strict separation. And finally, for defense in depth, always make sure your application connects to the database with the absolute minimum level of permissions it needs to do its job. That way, even if something goes wrong, the damage is contained. By using these defenses, we can slam the door shut on SQL injection. But security is a journey, not a destination. Eliminating this major threat just forces us to ask a new question. What other assumptions are we making about the data our application processes? And that's a thought you should always carry with you when you're building secure systems.